So I've got my power supply, we'll just turn it on, and I've got it set at 12 volts and 200 milliamps. There we go. I've got that feeding into my little DC pulse generator. This in fact is a J-car short circuit put it together yourself, and it makes a square wave output with a duty cycle about 50%, and out of that this is going to our coil setup. As you can see, I've got the blocking coil, I've got it attached to the blocking coil here, and then I've got the secondary coil there. This will pick up the flux on and off, as well as the current going into there on and off. I believe we need to have very high voltage, like really high voltage, to make a spark gap. And I do mean really high voltage, something like lightning spark gap or whatever. Yeah, beautiful, isn't it? Just out of the shed. So anyway, I'll turn it on and we can have a quick look. It's not, at these ratios, it's not actually blocking. You can see it's consuming most of the power. It's not actually blocking the flux. It's not actually, can I feel the hum? Not really, no. So really not much is happening there. Now if I connect directly to the second coil, we can see it's putting out 40 milliamps, which is pretty good. And if you listen closely, you'll hear that potentiometer doing a bit of a screaming thing there. I think 40 is the best I can get. Yep, it is. I'll just double check that. So just for simplicity's sake, I've turned everything down. You can see we're putting an output of 5 volts at 30 milliamps. Let's just switch that over to the secondary. And our secondary is putting out 7. So almost 8. So 25 and 7 make, it's putting out 32.5 milliamps, and input's 30 milliamps. Wow, that's interesting, isn't it? 30 milliamps going in, 32.5 milliamps going out. That's the whole theory. I think that's a bit unexpected. Let me know what you think. Well, that's no load, but you know, the theory's there, isn't it? Very interesting. So here I've got the first coil connected, and now I'm going to test how much each of these secondary and tertiary, etc. coils can put out. So the first one I've got here, as you can see, this one, that's 23.8. So I'll add them all up and then we'll find out what it can put out. So I've got it on the primary and it's showing 38.5 current draw, hence the loss in the voltage. But when I add all the induced coils up individually, there's all my numbers, we get a total of available milliamps of 57.74 milliamps for induction, which is a lot more than 30 milliamps there. Voltage doesn't matter because we can always multiply the voltage. Well, that's interesting, but what I thought was even more interesting is when I use the center coil as the drive coil, if you like, to induce the rest, obviously, all the figures are going to be a lot better. What I found was when I induced the center coil, the induction through all of these, that should be pressed up a bit, the added up induction is actually, I'll write it down for you, the available milliamps is 102.3, I think, milliamps. So twice as much, and that's interesting. So 102.3 milliamps when our draw is 30 milliamps. I thought that was interesting. There's got to be a way to add up these milliamps from each coil and use that. Let me know what you think. G'day, so what I decided to do was use a CD4051BE and this is a multiplexer. Collects them one at a time, combines them and then sends it out through pin 3. In this case this is an 8 gate, so we'll just be using 8 of these, so 4 on this side, 1, 2, 3, 4. Center tap, 1, 2, 3, 4. So those 8 induced coils will be connected to this multiplexer that will combine the sum of the power and, like I said, export it or put it out in one go in gate 3. So I thought I'd give that a go, but there are some things we've got to do to protect that CMOS. And that will include putting a diode across each coil so that our back EMF is mitigated. That's the first thing we have to do. So I'm using N4007, one N4007 diodes, and the way that we put them on is the cathode, which I'll just do a zoom in for you. Cathode, which is down on the left hand side there, you can see it's marked with the ring. That has to go on the positive end, and then this has to go on the negative end of our coil. So there we go. It's not pretty, but they're all on there, other than our center one, which we're going to attach our power to and induce 4 on either side. Right, thanks for the interruption, birds. So what I've done here, you can see I've put a diode across the coils, and that will negate to some extent the back EMF. Now the issue was this high voltage DC generator, which I tried using this. You might have seen it in a previous video. We were able to tune things, and look, it did work quite well. But I took the unprecedented step of buying a module, and here it is. I'll show you. There it is. And I reckon that this is going to do the trick, and if it doesn't, I'm going to use it for other purposes. So this is a high voltage DC pulse generator, and the input is, they say, between 3 and 7 volts or 3 and 8 volts or something, but 5 volts is the median, and it puts out 400,000 to 1 million volts. Little Chinese unit. That's pretty incredible, isn't it? So we have to test that, but that will be, so the leads here will connect up to our coil and pulse that coil at that high voltage via a spark gap. We'll have a spark gap going on. So yeah, that's looking forward to getting that going, and that will definitely shut off any flux from a magnet that we'll have there. So I'm looking forward to demonstrating that. Hopefully it works. Anyway, I thought you might find that interesting. Let's give it a go. So Max, I know it affects you, because I already just tried it, and it's pretty amazing. So we're just going to see if it's going to work. Now in actual fact, Max is very concerned about it, because it's just like lightning, isn't it, buddy? Righto, here we go. I'll turn the light off so you can have a look. She's a pearler. Just like lightning. So yeah, there it is. That's our pulse DC generator at work right there. Just one more time, just for fun. Yeah, that's fantastic. Thanks for watching, and I'll catch you later. It's all right, buddy. It's all right now. It's all over.